You're probably wondering, well, maybe you are, and if you aren't, just say you are. You might be wondering anyway, why double bonds and triple bonds count as one cloud, all right? And to understand that, we need to look a little bit more detail as to what a pi bond is all about. So this compound here, the common name is ethylene. Ethylene's formal name is ethene, which we'll talk about in the next section. But the important part for us here is that ethene, or ethylene, has a carbon-carbon double bond. So if you wanted to talk about the geometry around this carbon right there, that carbon is connected to two hydrogens, so that's two clouds. The double bond counts as a third cloud. It's going to be trigonal planar. So when you actually do this structure, the structure is actually flat. If we turn it on the side right there, you can see it's very two-dimensional, like a piece of paper. This is at 90 degrees, so you can see better what's going on. So something in that double bond is somehow contributing to the overall trigonal planar structure. And let's talk a little bit more about what's happening with these multiple bonds.
The sigma bonds in ethylene come from the overlap of sp2 hybrid orbitals, one from each carbon atom.
Remember that when you draw a Lewis structure, the first line you draw is always a sigma bond. So the little animation there in the lower right shows the sigma network in C2H4. So you can see that there's hydrogens, the little circles, that's the 1s orbital, and then the atom it's connected to is an sp2 carbon. And like we saw with boron, sp2 means trigonal planar. So you'd have three little sp2 hybrid orbitals. They're smacking together. They're making the little overlap, which is the actual sigma bond. So you can see sigma right there, sigma right there. Here's the sigma between the two sp2 orbitals on carbon, which is cool. Here's a sp, here's a sigma, here's a sigma. Those are the sigma bonds of C2H4, all right? But what we're going to do on the next slide is we're going to look a little bit more detail as to what's happening with the other bond. Because remember, when you draw a double bond, the first line you draw is sigma, and the second line you draw is called a pi. So let's look a little bit more about what's happening with the pi bond. In BF3, there was an unused 2p orbital. And for carbon, if it's in a trigonal planar environment, you're still going to have that unused 2p orbital. And this 2p orbital can connect to the other 2p orbital on the neighboring atom. This is a real interesting phenomenon. And remembering here that the 2p orbitals are always at 90 degrees, what happens when you make a pi bond is those unused p orbitals are like above and below the plane of the molecule. So let's back up a little bit. This is showing the 2s2, 2p2 atomic orbitals as they're being hybridized, in this case to 3 sp2 hybrid orbitals. And this part is why it's trigonal planar, because they're all the same energy and stuff like that. However, there's also this one extra electron in an unused 2p orbital. And that one electron in that unused 2p orbital is going to be used for the pi bond. And it does something really interesting. Now, it's kind of hard to see here, but this yellow blob is basically the trigonal planar. I've drawn it kind of coming out at the board, but you want to think about it as being flat. So it's like a flat triangle. And the unused p orbital sticks up a little bit above and a little bit below the triangle, all right? So, oh man, again, my drawing skills are just horrible here. But let's say you have like a triangle, and then it's kind of like a trigonal bipyramid, I guess. There would be an unused p orbital sticking out above and below the trigonal planar geometry carbon in the middle. And this extra 2p has an electron inside it. So if you have two of these 2p orbitals next to each other, they communicate with each other a little bit.
The pi bonds arise from the overlap of unhybridized p orbitals, one on each carbon. Note that pi bonding electrons are found in a region above and below the sigma bonding region.
So again, you've got these carbons, and they've got these unused 2p orbitals, which are above and below. So in the middle right here, this would be all of the sigma bonds, all right? And there's sigma bonds right there, all right? But the pi bond arises because the 2p orbitals are interacting with each other. And you can see in that video, it looked a little bit like bread. That's the closest thing I can use for an analogy here. And there's a piece of bread like on the top of the molecule, and there's a piece of bread on the bottom of the molecule. So a pi bond is those extra 2p orbitals like talking to each other. It literally is like it. And it makes an electron kind of spread above and below the molecule. In the C2H4 molecule, I like this description because the sigma network is kind of like the quote-unquote meat of a sandwich. All right, now, I'm a vegetarian, so I'm going to use vegetarian meats, but you use whatever meat you want to, okay? No problems here. But anyway, the sigma network is like the quote-unquote meat of the sandwich. And the pi network is the bread, and it's both above and below. You get 2 slices of bread per pi bond. Woohoo! Anyway, that's what makes this sandwich of C2H4. It's really cool. Now, this bread is what makes the molecule flat. All right, we saw pictures earlier. It was a totally flat molecule. That's because there's this pi bond both above and below the molecule, which is really cool. So backing it up here, I get really excited by this, you can tell. These extra 2p orbitals, in carbon's case anyway, are going to talk to each other on the adjacent carbons. And when they quote-unquote talk to each other, it makes a pi bond. But pi bond has 2 components. One part is above the molecule, and one part is below the molecule. All right? So a pi bond actually has 2 parts to it, and that's what we saw in that little video just now.
When we look at both sigma and pi bonds, we see that the CH2 fragments are coplanar and that ethylene is a flat molecule.
So this video shows the sandwich, quote unquote, the bread above and below that molecule. That's the pi bond. That's the second line we draw. And the quote unquote meat of the sandwich is all this stuff in the middle. That's the sigma network, all right? So it's really interesting. When you draw C2H4 as a Lewis structure, all right, initially you have just a bunch of single bonds. That's the sigma network. As you draw the second bond to make the pi bond of the double bond, that's adding a piece above and below the plane. And this pictures up here are trying to show it. So this part right here, that's the bread network, that's the pi bond. And again, the pi bond is both the light blue and the purple parts together. Pi bonds have 2 parts to them. And then all of this part right here, that's the sigma network, the meat of the sandwich, all right? And it's really neat how they all come together. So this is the combined picture of our sandwich, all right? And again, the blue and the purple is the pi bond. These little dudes are the hydrogens right here. Most of this yellow here is the sigma network. It's really cool how this comes together. Sigma bonds in valence bond are the first thing to form, and it's like the base part, the meat of the sandwich. And if you make a pi bond, then it's like bread above and below the structure of the molecule. This pi bond makes these molecules flat in this region. Pretty exciting. Acetylene is C2H2 in acetylene torches. The official name for acetylene we're going to see in the next chapter is ethine, but we'll talk about that later. Ethine is HCCH, and when you draw a Lewis structure, this has a triple bond. So get ready, all right? The first part right here, the first yellow box, shows the sigma network in acetylene, all right? It shows just the hydrogen carbon sigma bond, which is right here. Here's the carbon-carbon sigma bond between the 2 carbons, and here is the other carbon-hydrogen sigma bond. So this part right here would be like the HCCH part right there. It's just showing the sigma bonds. But the Lewis structure, which is over on the left-hand side right here, the Lewis structure has not just 1 pi bond, but 2 pi bonds. Remember, a double bond is 1 sigma plus 1 pi. A triple bond is 1 sigma plus 2 pi. two pi bonds. And in this case, it's going to make two of these slices of bread. So the picture, the yellow box on the right, this is the first pi bond. You can think about it as bread above and below the acetylene molecule. But get ready, this is kind of cool. This is the second pi bond. It also has two components, but instead of being above and below, it's like left and right of the molecule. So you try and draw this like it is right here. It totally fails because there's too many bonds like all coming together, man. It's a crazy sandwich. But again, you can think about this as like some kind of super sandwich where instead of having just the bread above and below, now you have the bread to the left and the right as well. Mega sandwich. But anyway, sorry, that's I must be hungry. Anyway, Prof hat back on. C2H2 is different than the last one because there are two pi bonds. And so one pi bond will be above and below, two components per pi bond. The other pi bond will be left and right of the molecule. And again, in the middle is where all the sigma network happens. It's pretty cool how this stuff comes together. So this is why now in a Lewis structure, you think about double bonds and triple bonds as just one big cloud, because these pi bonds just kind of add on to the already existing sigma network. It's one big cloud of electrons, whether it's double, single, or even a triple bond. It's just bigger and bigger clouds, basically, that you have to deal with. How many total sigma and pi bonds are in acetylene, C2H2? All right. Well, I covered up the picture there, so let me draw. What you would do, first of all, if this was your problem, is you'd want to draw the Lewis structure for acetylene, aka ethylene, and stuff again. And when you do that, it looks like this. It has a triple bond between the two carbons, and there's single bonds between. Now, the triple bond, like we said, is two pi's and one sigma. So each of the lines is a bond. That would be 2 pi and 1 sigma right there, all right? And so it's tempting when you're doing these kind of problems to answer, for example, B, because that's it. But the whole molecule also has a sigma bond right there. And over here is another CH sigma bond. So if you count it up, there's actually 1, 2, 3 sigmas and 2 pi bonds. The answer is D. So I put this up there because if you'd happen to see a problem like this in the future, don't forget to count the CH sigma bonds, or maybe there's a CH3 or something like that. Look at the whole molecule, not just the double or triple bond. Another interesting factor when it comes to double and triple bonds, a single bond can be rotated very readily. So this picture right here shows a carbon-carbon single bond, and carbon-carbon single bonds will rotate readily. But if you have a carbon-carbon double bond, it's very difficult to have the double bond twist. So if you wanted to put, say, this hydrogen right there and this hydrogen right here, probably would be very difficult to make it happen. And that's going to be important for us here in a little bit. We're going to consider in Chem 222 that single bonds have free rotation, which means they rotate like propellers very easily. But we're going to also assume that double bonds, and triple bonds for that matter too, don't rotate. You have to break that pi bond. You have to rip the bread in half, essentially, rotate it, and then reform the bread. And that's a pretty high energy process.
The carbon-carbon double bond prevents the ends of the 2-butene molecule from rotating freely relative to each other. As one end rotates, the energy of the molecule increases greatly because the carbon-carbon pi bond must be effectively broken. That is, there is a large energy barrier to rotation around the carbon-carbon double bond. Butane can rotate easily about its carbon-carbon single bond because the atoms of its methyl groups repel each other rather weakly. Rotation about this bond is accompanied by a small energy barrier and occurs readily at room temperature. The two sides of the molecule are therefore constantly spinning with respect to each other.
Lots of things in this video we need to talk about. First of all, the upper left-hand version has a double bond. That molecule has a carbon-carbon double bond. And in the lower right corner, that compound has just carbon-carbon single bonds. And if you look at the difference in energies, all right, like for example, on the upper left one, 233 to 26, well, that's about 230 and 30. So it's about 200 kilojoules per mole difference, roughly, between those two values. In the lower right-hand corner, it's 78.49 is about 80, and the other one's about 20. So 80 minus 20, it's about 60 kilojoules per mole difference. And there's a big difference between 200 kilojoules and 60 kilojoules. And that is what allows the single bonds to rotate pretty readily. So we assume that compounds like butane or N-butane will rotate readily, all right? There's differences here in the energies, and that's something you'll talk about in organic chemistry, which is the second year of chemistry. At this level, we don't need to worry about like why there's a small gap and then a big gap and then a small, and that's for your organic chemistry class. But anyway, it's relatively easy to rotate a single bond. On the other hand, the double bond, which is up here, you have a much larger energy gap to make that happen. There's two ways to name these kind of compounds, especially the upper left one. The old way was trans-2-butene, but the current trend is to call it trans-but-2-ene, and this is something we'll talk about in the next chapter. Likewise, in the bottom, butane technically would be N-butane, and we'll talk about all of this later. But regardless, the important part is that if you're trying to rotate a double bond, it's probably not going to happen. It's much higher in energy to make that transformation occur. On the other hand, single bonds will rotate very easily, and this will have implications for stuff we'll talk about here pretty soon.